So let's talk about conductors for a few videos before moving on to dielectrics. So first we're going to consider the case of a conductor which is isolated and under static conditions. And so what this means by isolated is our conductor isn't going to be part of some circuit, so it's just sort of floating in space, we can think of. And in terms of static conditions, we can say we have some electric field that the conductor is in the presence of, but that electric field is not varying over time. So maybe we have some external electric field that looks like this. And so again, these are all going to be our electric field external, and that's going to be time invariant. And so what's going to happen is that this E external is going to cause our free charge carriers to migrate very quickly. So E external causes charge carriers to migrate quickly. And of course, we know that our positive charges are going to want to move in the direction of our electric field. Our negative charges are going to want to move in the other way. So if we're talking about just electrons, we're going to have all of our electrons move over here towards the left, and we're going to have a net positive charge left over here on the right side. Now, this charge is not actually inside the conductor, but rather it's going to be on the surface. So right on these surfaces, we're going to have a negative charge on the left surface and a positive charge on the right surface. And one other thing to address too is I've mentioned quickly, so that's pretty vague. How quick really depends on the sigma. If we consider an ideal metal, which has an infinite conductivity, then this movement of our charges is going to be instantaneous. And of course, for good conductors, good metals, this charge is going to be so quick that for all intents and purposes, we can essentially assume it's instantaneous. So again, let's sort of write down some of these things that we're saying. So our free charge carriers are going to accumulate on the conductor's surface. So as I've drawn above. And so again, note that it's on the surface, not actually inside the conductor. So free charge carriers are going to accumulate on the conductor surface. And so we say then that we have something called an induced surface charge. So this external electric field has induced some surface charge. So on the left side, we have some negative surface charge. On the right side, we have some positive surface charge. So remember, anytime we have separation of charges, that's going to create an electric field. So we have charge separation now inside our conductor. So charge separation, which is going to induce an electric field. And so we can call that induced electric field E induced. So if we come up here and draw this, so let's do it in a different color so it's easier to tell the difference. So we have some E induced, which is going to be pointing in the opposite direction of our external electric field. So that's going to be our E induced inside of our conductor. And so inside the conductor then, what's going to happen is that E induced is going to cancel out our E external. So let's say this E induced cancels out that external electric field inside, so very important, only inside the conductor. Okay, so let's sort of redraw this then. So what we have is our conductor, and so no, that's not necessarily the same size, but let's see, there we go. So we got something that looks like that, and so now what we're saying is we don't have any electric field inside there. We have some electric field that is on either side of the conductor, so it's outside, but inside that's being canceled out by the induced electric field. So this is still our external electric field, E external. We still have these charges. So we have some negative charge on the left side, some positive charge on the right side. But again, keep in mind that's actually on the surface, that's not inside. And so what we can say then is our net electric field in here is going to be 0. Okay, so let's sort of make a couple other general statements now. So if we consider Gauss's law, or Maxwell's first equation, so Gauss's law slash Maxwell's first equation, which of course related our electric flux density to our charge density in a volume. So Maxwell's first equation, we can say if that electric field inside that region is 0, then what that means is our charge density in that region has to be 0. So this is in the conductor, because our electric field is 0 only in the conductor. So we can come up here and we can say that our rho v inside is going to be 0. We can also consider our relationship between our electric field and voltage or potential. So we can say our electric field we know is equal to negative gradient of V, and we know that that has to be equal to 0. So what that tells us is that our potential is going to be the same at every point inside that conductor. So potential is the same at every point in our conductor. And so another way to say that, which we'll often write, is we can say then that our conductor is an equipotential body. So conductor is an equipotential body. Okay, so sort of just to summarize those three key ideas, if we're talking, and so I should have clarified too that this E equals 0 inside and rho v equals 0 is going to be for a perfect conductor. And oftentimes we're going to approximate our good conducting metals as perfect conductors, because as a first approximation, that's a really good approximation and can make things a little easier in terms of our analysis. So again, as I said earlier, for a perfect conductor, we have a sigma equal to infinity. So in that case, then, we have E is equal to 0 inside our conductor, rho v is equal to 0 inside our conductor, and VAB is equal to 0, where A and B are just any 2 points in our conductor. So for instance, coming back up here, we could say maybe this is point A, this is point B, we could say other points, C, D, so any points in there, the voltage between those points are going to be 0. So that covers our conductor when it's isolated and in static conditions. And what we're going to look at in the next video is what happens when we apply an external voltage to a conductor.